So we are still trying to prove that angle ABC is half the measure of the arc length of AC. But what's different about this case is that our point is no longer on this line here, but it's actually on the interior of the angle. So what we're going to want to do is first show that the diameter is represented. So we're going to create a line segment from B that goes through the center of the circle, which is Q, and we're going to place that here. So now what we see is that we've kind of divided this angle ABC into two different ones. So now we know that this total angle ABC is equal to ABD plus DBC, and we know that the arc AC is going to equal AD plus DC. And we also know from our first case that ABD is going to equal half the arc length AD, and the same can be said for angle DBC. And that is just because of these isosceles triangles that are created when we connect the center to our other points, and we have these congruent radii for these two legs right here. So now that we know the values of ABD and DBC, we can take the information that we already have that we can, split up this angle and split up these arc measurements and use substitution of these into this equation here to kind of get where we want to go. So substituting, we see that ABC equals ABD and DBC, which we already knew. And so when we substitute that in, since ABD is half the arc length of AD and DBC is half the arc length of DC here, we know that this sum is going to be half the arc length of AC, and that concludes our proof.